Hello everyone. Okay, in the last lesson we saw how to simulate epidemics using the SIR model. But in that case we were using parameters that we were choosing ourselves. In this new lesson instead we will see how to estimate these parameters directly from epidemic data. So usually when we get data regarding a real epidemic, we can either use some parameters taken from the literature and then create a simulation and see if it matches the real data, or we can use the data itself to estimate the model parameters. Actually, usually it's common to do both things because some parameters like the transmission parameters are usually taken from the data, but other parameters like gamma, which are less variable between different scenarios, they are usually taken from the literature. Also, this helps us get better models, but we will see this later. So, which are the steps to estimate model parameters? Okay, first we of course acquire the case data. We can also acquire other kind of data like the number of tests, the number of recovered people, the number of hospitalized people. We can acquire as many data as we want. Actually, the more we have, the better it is. Then we choose a model that describes the data. In our case, we saw the SIR model, but there are plenty of them. Either more complex kind of SIR models or something totally different. Finally, we estimate the parameters, but once we estimate the parameters, we need always to evaluate them with the real data through ulterior more simulations. Once we see that the parameters are good, we can then take some insights from our parameters like the R naught, the herd immunity threshold, the prevalence, the predicted prevalence, etc., etc. So there are many ways to estimate parameters, but we will focus on two of them, which are quite standard and much simpler than more modern techniques. I will show you a method called mean squared error minimization and another method called likelihood maximization. First, mean squared error. So to estimate the mean square error, it means to estimate a parameters through mean square error. It means that we want to find the set of parameters that minimize the error between the predictions of our model and the data itself. What does it mean? Let's take, for example, a very simple model, a linear regression. The blue line are the predicted values and the violet line dots are the observed data. While the red lines are the error. We want to find a model, so a line for in this case, that minimize the sum of these errors. But since these errors are both positive or negative, we take the square of them in order to have all of them as positive values. And we see the same concept here as a mathematical notation. So ft and the theta, it's a function that given some input, in our case time, because we follow an epidemic through time, and some parameters, theta, a set of parameters, then it produces some predicted data. In this case, we want to compare the data predicted by this function with the real observed data, we call it y, which we have for each time point. Mathematically, then it means that we want to take the difference between these two values, take the square in order to have them all as positive values, sum of them throughout all the time point in our epidemic, and then take the mean. Finally, we want to find the set of parameters, theta, that minimize this function. This is the meaning of argmin, is that we want to find the set of parameters, theta, that minimizes this function. The other method is called maximum likelihood method. It's based on probabilities. And the concept is that we want to maximize the probability of the data given the parameters. The probability of data given parameters is also called in jargon the likelihood. You can see here that we have a certain distribution, and we want to maximize the likelihood of the data, which is this red line, given some parameters. And it can be seen that, for example, these parameters equal to 3 is the point in which this likelihood is the maximum. More formally, it's all about taking again the probability of the data given the parameters, and we do this for each time point. That's why we have the t subscript here. But then how do we join this probability along all the data that we have? Simply we need to take the product of them, because this is something called a join probability. So the union of probabilities for independent data points is given by the products of these single probabilities. This equates to the likelihood of a data set. But this can be problematic for computers, because once we take the product of many probabilities, the final number gets exponentially smaller. And for computers, computers are not able to work with numbers which are very, very, very close to 0, because it creates some problem called underflow. So the computer just cut them to 0. So it's common instead to work with the log likelihood. So we take the logarithm of this probability, which transform a number from 0 to 1 to a number from minus infinity to plus infinity. And then instead of taking the product, we can just take the sum, which is also easier to manage. So we maximize the sum of the log probability of the data, also called the log likelihood. Okay, but what does it mean, P of these values? Well, this is, again, a probability function, and we can have different probability functions for different kind of data. For example, when we have data which is continuous and can go from minus infinity to plus infinity, it's usual to use normal distributions. For example, if we take the differences from one average value, they are either positive or negative. If we have continuous values, but that can only go from, they can only be positive, it's usual to use log normal distributions. For example, laboratory values, they are usually log normal distributed. Of also many physical parameters like age, weight, they all cannot be lower than 0. But sometimes we don't have continuous numbers, but we have events. So in this case, we use the binomial distribution if the events can be either yes or not. Or if we have a count of events, for example, the number of fishes that you can get while from the sea in a given day, we use the so-called Poisson distribution, which is funny because Poisson means fish in French, but it actually comes from the name of a guy. It's not. It doesn't come from the fish in French. Sometimes we assume that for a given day we have a similar rate of a certain event, or we have similar rates in a large territory, and so we can use a Poisson distribution. But if we expect the rate to be much variable between different territories, different cities, then maybe it's better to use the so-called negative binomial distribution, which assumes that there is more variability in your data than expected from a Poisson distribution. Finally, if we're working with waiting times, usually they are exponentially distributed. In practice, since with SIR models we count cases, it's usual to use the Poisson distribution, or we can use the binomial distribution if we have a number of cases which is very close to the total population. Which is the difference between the two methods? Well, the MSE, it's easy to compute manually. It's also quite old historically. You can do it really just by hand. Therefore, it's also easy to interpret. But also, it is the problem that it can be quite biased for when we have the initial or the final phases of epidemics, because again, cases are integer numbers, and this means that our model will not work well when you are so close to zeros. Also, it can for this method, it's totally fine to have negative cases, which of course is not realistic. On the other hand, maximum likelihood estimation is much more flexible, because you can have different kind of functions, likelihood functions for different kind of data. And therefore, you respect the data nature. So if something is integer, you use a distribution for integer values. If something doesn't go below 0, you use a distribution that doesn't go below 0. It also allows you to consider different data sources, because you always have a probability out of it. So you can join this probability together and have one unified score, even if the data sources are very different between each other, which is instead is not the case for mean square error, in which you need to find a score which is on the same scale between the different data sources in order to join them. But of course, there are drawbacks also for this methodology. First of all, it cannot be computed manually. It's very hard to do it. And so you need to know the algorithms that you are using, and you need to trust them. Second, you need to know which likelihood distribution to use for each data. So you need to know which are the probable values for this data. You have to know how much variability there is in the data. So you need to be a little bit more expert about the problem that you're studying, while MSE, it's a more generalized methodology. Also, MLE may need more data than MSE. But the two gives the same result in one condition. If you use MLE with a normal distribution, that it equates to use MSE, because MSE mathematically can be shown to be a special case of MLE when using the normal distribution. So let's move to the practical part. Again, we will use R, and I will assume that you already followed the precedent lesson on model simulation. And let's load the required packages. They are again the same of the previous lesson. So the solve for solving differential equation, the plier and tidier for manipulating data, and ggplot2 to plot the data. To estimate some parameters, we need data, of course. But instead of using real data, of which we don't know the actual parameters of the epidemic, we will simulate our data. There are positive and negative aspects in doing this for this tutorial. The positive aspect is that we will be able to see if our estimation method works, because we know the parameters that generated our data. The negative aspect is that in reality, data is never as nice as the one that we simulate ourselves. So our result will be overly optimistic. Extremely optimistic, I would say. So to simulate the data, let's start as usual from initial condition. So population of 1 million plus 1 infectious case. Some parameters, I took beta equal to 1 and gamma equal to 1 over 8. So this is the last 8 days. So gamma is 0.125. And then we follow the epidemic for 60 days. As we saw in the previous lesson, we need a SIR model function, which is again the standard one that we used as first example in the previous lesson. So we have the calculation of lambda, which then is used to estimate the differential change in the susceptible, the differential change in the number of susceptible, infectious, and recovered. And this is the output of this model. We already saw this output in the previous lesson. But now we need to create from this simulated epidemics some data which is a little bit realistic. First of all, because the data that we simulated will be continuous. We said before that these compartment models produce a continuous number of cases. It means that you can have a fraction of person that is infected of is susceptible, which of course doesn't happen in real life. This is the so-called mass effect assumption. So we need to transform this number into integers in order to transform them into a real number of events. But before this, we also want to add some noise to our prevalences, because data in real life is never so clean, so doesn't follow an exact curve. There is always some noise, because sometimes more people come and get tested, and other times less people get tested. Sometimes you can have small local epidemics, and so on and so on. So we want to simulate this noise by adding again random noise to the mean estimates of the simulation, but also we will have a noise that scales with the prevalence. This is common for this kind of data, that the noise is not always the same, but the more cases you have in your epidemic, the more random oscillations you will see in the data. So we add the noise and then we transform them into integer. To transform into integer, we have two possible approaches. The simplest one is just to round them, but this is not very a correct approach. It will create some bias. Also because in reality, the data that we simulate with the SIR model is average data. It's like we are saving data from thousands of alternative realities, and the simulated data is the mean of these alternative realities. So a correct approach is to use this mean as the rate for a Poisson process that then create a random realization of this ideal reality. It also adds some extra uncertainty, which is good to test the robustness of our methodology. A third aspect to keep in mind is that in order to better evaluate the goodness of our estimation methods, it's a good idea to estimate the parameters on a subset of the data instead of on the whole data, and then evaluate them on a part of the data that wasn't used to estimate them. This allows us to estimate the so-called out-of-sample error, and also allows us to avoid overfitting the data. Overfitting means that you estimate parameters that are extremely predictive for the current data that you're observing, but then once you get new data, they don't work anymore, because they are fitting not just the real signal, but also the noise behind the data. Okay, how do we create this simulated dataset? Let's go step by step. Okay, we start from the mean prevalence that we simulated with the ODE model, and we add, as we saw before, we said before, the random noise distributed as a normal noise. This normal noise will have a mean 0. But we'll have a standard deviation which scales with the size of the epidemic. So you can see below in the plot of the data that here the dots follow quite closely the curve, but then here the noise increases. Once we have the average number of average prevalence with some extra noise, then we can use R Poisson to generate the random number of cases. Again, this is how we create a Poisson process. We pass it the average prevalence, and it will create integer events, number of events. So finally, we create our dataset with this simulated data. we have the time, which is the same for the simulated dataset, and then the new generated cases. But also, as we said before, we want to create a subset of this data to estimate our parameters. Therefore, I subset this dataset using filter from the dplyr packages and selecting only days, only the days above the 10 and the days below 30. And then we use our plot model function that we saw in the previous lesson to visualize the simulation. We don't pass the simulation as it is, but we first we just use the number of cases, because we are not interested in the number of susceptible and recovered individuals in our simulation. Once this function will create the usual red line, which is the number of the average number of cases. But then we want to add the points related to the simulated data. We can do this by just using geonPoint, another common layer in ggplot. And using the data argument, we can use different data from the one used in the general plot. And then again, using the static, we can set up some extra information. And we have here a nice overlay of the average trend and the simulated random data that we actually observe in real life. Okay, once we have the data, we need to perform the actual parameter estimation. What does it mean to estimate parameters? Technically, it means to take an objective or target function, you can use both names, and to either maximize it or minimize it, depends on the kind of function. In R, the most used function to do this is called optim, which is included in the base installation, so you don't need any packages for this. What does it mean to optimize? Imagine that this is our parameter space, that is a sort of dimension of space created by our parameters. Imagine that this is, for example, beta, and this is, for example, gamma. And Z is the outcome of our objective function, which can be MSE or ML, maximum likelihood. Let's take MSE because we minimize MSE. And this optimization function, they do try various values of x and y, trying to look the point in the parameter space that minimize this function. In this case, it's quite simple because it's so-called a convex problem, and so there is one single place, which is the best, the minimum. But in real life, often you have much more complex landscapes with multiple minimum and maxima, and sometimes optim is not enough to find a solution, the best solution for the problem. Okay, so which are the steps that we need to do to create the parameter of estimation? So first of all, we need to choose our objective target function, which in our case is either MSE or ML. And then this function will do a number of things. First, it will take the parameters suggested by optim. So optim will suggest to this function different values for beta and gamma every time in an iterative loop. With this beta and gamma, we will need to create a new simulation, and then we will compare this simulation with the observed data using, again, either MSE or ML. Optim will get the result of this comparison, see if it's good or bad, and produce a new combination of parameters to evaluate. And the function will explore various combinations until it will reach a place in which it thinks that we found the minimum or the maximum of the problem. You don't need to think a lot about initial values, but they need to be somehow close to what we expect to be the real parameters that we want to estimate. Sorry, I forgot to mention that these functions will suggest parameters in every iteration, but the first group of parameters need to be suggested by us. They are called initial values. And as I said before, you need to pick them in order to be in the ballpark of the expected real parameters. In this case, I chose beta equal to 1 and gamma equal to 1, that is R naught equal to 1. Okay, let's see the algorithm for mean square error optimization. It seems complex, but we can go step by step. Okay, first of all, we use the parameters that are produced by Optim, this one, params, which are passed to this function, and we put them into the usual ODE function, which also uses the initial condition, the SIR model, and the days, which are defined in the global space. Usually it will be a better idea to pass these parameters also here, but I didn't want to complicate the code. It's a good idea because if we pass the parameters manually, then we know exactly which parameters we are moving around. Otherwise, if we use parameters that are in the global space, maybe they get changed by other function, we don't realize it, and then we have biases and we don't know where they come from. But in this case, I just wanted to simplify the code. Once we simulate the epidemic with the parameters suggested by Optim, we need to extract the epidemic values, so in this case the prevalence, which happens in the same days of which we have the data. Because remember, our data is a subset of the 60 days of epidemics. We just have data from then day 10 to day 30. Or sometimes we may have holes in the data. So we need to make it so that the simulated data and the observed data are taken in the same days. It's quite easy to do in this case. We just need to subset the times which are also in the actual data. And we save these values into this variable. Then, as we saw before for MSE, we just need to take the difference between the predicted cases and the observed cases, make the square in order to make them all positive, and then sum them. This is called sum of square errors. Before I said that we will use the mean square errors, but if you think about it, in this case, the number of observation is fixed. It doesn't change between iteration of the optimization function. So it doesn't bring any extra information. We can just remove the divided by n, the denominator, because it's always the same. And therefore, we create this value, the sum of squared errors that we return. Once we have this objective function, we pass it to Optim together with the initial values and some extra data. Optim can take every number of extra parameters, custom parameters. So for example, we would have passed the initial values here, we could have passed parameters that don't need to be optimized, and so on and so on. And this is the kind of output that we get. It's a list in which the parameter element have the final optimized values of the parameter of interest. You can see they are quite close to the real parameters, even if we used a small fraction of all the data points and we added noise. So beta in the original beta was 1 and we have 0.99. The original gamma was 0.125 and we have 0.123, so it's quite close. This value, there are a number of technical extra informations here. This value is just the last value SSC at the last evaluation. This one function is a little bit more interesting. It tells us how many iterations Optim needed to find the best solution. It's a way to understand if the problem was easy or the problem was hard to solve. If the number of function evaluation is low, it means that either our initial values are very good or the functional landscape is very simple. In this case, it's convex, so Optim didn't have any problem in find the best point. Gradient is not used in this case. It can be used if we use different algorithms apart from the default of Optim, but we won't describe this now. Instead, it's important to see this parameter here, convergence. If it's zero, it means that Optim was able to find the best solution for this problem. If we have other numbers, the other numbers may mean a lot of different problems with the convergence. In the first slide, I told you about convergence. It can happen sometimes that we don't have enough data compared to the number of parameters to find the best solution. So we can have either situations in which the Optim is stuck in a suboptimal minima. For example, if we have a very complex landscape in which we have a minimum, but we have also some local minima, the Optim may be stuck here instead of reaching here. Or also it's common that Optim is not able to find the best set of parameters because there are multiple combination of parameters that give you the same results. To make a simple example is imagine that we have a value of BMI, body mass index, and we want to know from which combination of height and weight we got this body mass index value. Of course, it's impossible to know because many combination of height and weight can produce the same body mass index. One can be very tall and weight more, or can be very short and weight less, and give out the same BMI. This is related to what I told you at the beginning, that it's usual to use optimization just for some parameters like transmission parameters, because they can vary a lot between different settings, and keep other parameters like gamma from the literature, because they are more related to the pathogen itself and they don't change much between populations. This will have convergence, like for example, in the example of the BMI, it will be like fixing the height. Then if we have a fixed height for a certain level of BMI, there is just one weight that can produce it. So by fixing parameters which we are more sure about, we can help the algorithm converge even if multiple combination of parameters can produce the same results. Let's move now to maximum likelihood optimization. Okay, this part is exactly the same. That is, we simulate trajectories using the parameter values produced by Optim, and then we subset the trajectory using the data point that we have in our data set. Instead, this part is different. To get a likelihood value, there is a family of functions in R. All start with D, which means density, and then we have Poisson for Poisson, norm for normal, binom for binomial, beta for beta, and so on and so on. And they will provide the likelihood of the data given some parameters. In this case, the data is passed as first argument, so x, which is the number of cases, observed number of cases. And then the parameter of a Poisson distribution is called lambda, which is the rate. And we put into lambda the predicted number of cases from the ODE model. Again, remember to set log as true in order to avoid underflow problems. And if we set log as true, instead of using a product of this probability, we just use the sum. That's why I used LL here. It means log likelihood. One last thing to be noticed is that Optim tries to minimize a function, but in this case we want to maximize the likelihood. But this is simply solved by putting minus in front of the likelihood. Again, this part is the same, and we get our output, and we can see again that the predicted values for beta and gamma are quite similar to the real ones. That is 1 and 0.1.5, 125. Actually, for MLE, they're a little bit better than for MSE. Also, we can notice that MLE needed less evaluations than MSE to reach the optimum of the function, 77 here, 71 here. And since the parameters are totally the same, this is a way to tell us that MLE was working better than MSE for this problem. But once we get this, we estimated our parameters, as we say, we need to evaluate them. We need to compare them with real data to evaluate the so-called goodness of fit. In our case, this is not actually needed because just by looking at the numerical values of these parameters, we know that the estimation works because we know the actual parameters behind this epidemic. But in real life, we don't know the real beta, real gamma. So the only way to more or less understand if the simulation, the estimation is working well, is to compare the estimated parameters with the real data. Let's do how to do it in our situation. Okay, first of all, we use the parameters estimated using the optimization algorithms to create new trajectories using the usual ODE function. And instead of putting the parameters ourselves, we take the parameters either from MSE or for MLE, so that we have two trajectories. Then we join the data from these two trajectories into one single data set. We just keep the number of infectious cases. We don't care about susceptibles and recovered individuals in this case. And just give a different label for the different simulations. And then we plot this data. Again, it's the usual ggplot syntax. So we first created the general plot in which we use this data plus, and we said that we put the days on the x-axis and the cases on the y-axis, and we color the lines by the source, by in this case the estimation algorithm, either MLE or MSE. But we also add extra data to this plot. So we use the original simulation data as ground truth, which we plot as a single thin line behind the new estimated data. In real life, we don't have this, of course, with this real epidemic data. It's unknown. Then we add the lines estimated through MLE and MSE. If you can notice that I made a little bit transparent with alpha. Alpha is a parameter that in which 1 means that a line is totally opaque, totally visible, and 0 is totally transparent. I put them a little bit half transparent in order to let us see the real trend below. And also put size equal to 2 to make them a little bit larger. Finally, I add the real data, the simulated data that we have, the random data, to show how well are they fitted by the model simulated on the estimated parameters. And we can see that in both cases, the estimated parameters produce very well behaved simulations, both in the zone in which we have the data, but also and especially, this is important, in the zones in which we don't have the data. This is a good indicator that the estimation worked well. But of course, this is really simplified situation in which the model that generated the data is very simple and there is not much noise and so on and so on. In real life, it's very hard to expect such good fitting in places in which we don't have data. Okay, thank you very much.